in the same way, with the one that we had, not this one, but the one that we had, which was D is an I, E is an I, but D union E is not an I.
Right.
So the only question is, what do you do with the first part, D parallel to D? Because D union D is an I. So what I added, I don't know if this is just cheap, but I said, if D not equal to
That seems like a valid case.
So, for the first, the independent set, I was saying, I said, D is an I, and E is an I, as sets themselves, but D union D is not.
Right.
And the only problem with that is reflexive.
Well,
So
no, that's fine. We can do a lot more business. D union D is such that D, comma D.
Wait, how are you supposed to spell B, Y, C?
Okay.
Okay, let's get started. So last time we talked about duality, and the topic of the class today is going to be duality for linear matroids. Okay. And before I talk about duality itself, I want to go back to something that you guys did for homework number 1, which is the matroid of a linear subspace of a vector space. So in one of the questions in homework number 1, I defined for you guys what it meant, what the matroid of a subspace of a vector space was. And I wanted you to show that linear matroids were precisely the ones represented by subspaces of vector spaces. Okay? And I want to revisit that. So let's say that you have some k-dimensional space in Rn. And let's say that we have a fixed system of coordinates on Rn. Okay. So what you guys showed in homework number 1 is that there is a matroid that you can associate to this vector space. There is a matroid M of V such that if you take any basis of V, so if the rows of a K by N matrix A span V, then this is the matroid on the columns of this matrix. Then the columns of A when you consider the columns as a collection of vectors, the associated matroid is this matroid M of V. So you guys showed this in homework number 1, but I want to do a different proof from the one that most of you did. And this proof you can see, I posted in the course website. This is the solution of Alex Fink. And I want to talk about it because we will need it. The question is this. The point of this exercise was that it doesn't matter which basis you choose, which matrix A you choose, you're going to get the same matroid. And so that must mean that we should be able to describe this matroid without talking about A. But we should be able to describe it only in terms of B. Because it doesn't depend on A. So, question, can we describe this matroid only in terms of A? In terms of B? Sorry. Without reference to A? Because remember, what we did is we said, we defined this matroid M of V as the matroid on the columns of any matrix that generates V. Okay. But I would like to talk about how we can actually describe this M of V without talking about the matrix, just talking about the vector space. Okay. And so this is what I'm going to do. So just to make it a little bit simpler, let's talk about case k equals 3 and equals 5. And let's say that you want to define M of V. And for now, the description that we have is that we pick a basis and we put it in a matrix. So A is a matrix. It's a 3 by 5 matrix. And the columns are C1, C2, C3, C4, C5. This is my 3 by 5 matrix. Okay. So M of V is the matroid on the columns. So now the point is that I want to describe this matroid without referring to A. And so let me say this. Imagine that you take some subset of the columns. Let's say, I don't know, 1, 3, 4. And you want to know whether that's a basis. So C1, C3, C4. Is that a basis? Well, here's one way in which you can do this. Let's look at the matrix A. And only pay attention to those columns, C1, C3, and C4. And instead of putting C2 and C5, we're going to put 0 columns there. Okay. So here's 0, and here's 0. That we call this matrix A. 1, 3, 4. Okay. So when are C1, C3, and C4 going to be a basis? Well, if the thing generated here has rank 3. In other words, if and only if this guy has rank 3. Right? Okay. In other words, the dimension of the row space of my matrix A1 3, 4 is 3. Okay. But now I want you to notice something, which is that I can describe this row space without referring to the matrix. Because I can say, look at the projection. Let's look at this, consider this map. I mean, basically what I want to say is that the row space of A1, 3, 4 is basically the projection into the coordinates 1, 3, and 4. Okay. And so that's what I'm going to justify. So consider the projection pi from R5 to, so the projection that takes the point with coordinates x1, x2, x3, x4, x5, and sends it to only coordinates x1, x3, and x4, and sets the other ones equal to 0. Okay. So this is
from R5 to R5, really.
it's from R5 to R5, but
yeah, but the image is going to be small.
what's the image? The image is something that I'm going to call U134, or let's call it X134, which is the collection of points that have some coordinate here. This one is 0, some coordinate here, some coordinates here, and this one is 0. Right? So this is the projection of the whole space into the coordinates 1, 3, and 4. Okay? So the rows of this guy, the rows of A134, are basically the rows of A projected under this map. In other words, the row space of A134 is just what you get by putting this equal to 0, this equal to 0. So it's precisely the image of my vector space V under this projection map. Row space of A134 is simply the projection of V, this projection. And just to make clear which projection this is, I'm going to call it pi134, the projection of R5 into those three coordinates. Okay. Row space of A134 is pi134 of V. So C1, C3, C4 is a basis if and only if the dimension of the row space of A134, which is this projection, is 3. Okay. And this is a statement that is completely independent of the matrix A. It's just a statement about the vector space V and how it projects under this projection map. Now let me say this in an equivalent way, which is that if you look at the restriction of the projection map, so let's say you only project the things from V. So the restriction of the projection map to V, we know that this guy is three-dimensional, right? So the image is three-dimensional. The image of this map is three-dimensional, if and only if this is an isomorphism. It's a bijective map between these two three-dimensional spaces. So this is true if and only if this map is bijective. And any questions about this so far? So, in other words, what I'm saying here is that what are the bases of my matroid M of V that I'm trying to describe? They are the subsets S for which this projection map is bijective. I call this one pi 134. Pi sub s in general will be projecting into the coordinates in S.
So they're subsets of coordinates.
Subset.
Are the subsets S of. So let's say V is a subspace of Rn. So these are the subsets of 1 up to n,
Yeah.
such that projecting under those coordinates is a bijection. The projection pi sub s going from V into, here I called it x134 in general.
X sub
I'm just going to call it xs. Is bijective. Questions about this? Is that clear to everybody? So let me ask you something now. Why? I know that in the statement of the problem, some of you were confused about this business of having a fixed system of coordinates. So why do I need a fixed system of coordinates to make this definition? Is that clear to you guys?
Otherwise, you don't know what 1 through n are referring to your system of coordinates x1 through xn. You're taking subsets of which of those you can project into. So if you switch them around, then your s1 through sn have a flip.
Exactly. I mean, the point is that how do you define these projections? You define them in terms of saying, let's project into coordinate 1, 3, and 4. That already assumes that you have a system of coordinates. And that's why to define this matroid, you have to take a vector, a subspace of Rn, and you have to take a fixed system of coordinates to decide which these projections are. For example, this set x134. What is it? It's the collection of vectors having non-zero coordinates in instances 1, 3, and 4, but that's with respect to the canonical basis that you started with.
Thinking back on that problem we had before, I'm just thinking, what if the columns, what if they actually, some of the columns were dependent? So your independent set actually didn't have like the zeros in it, but your independent vectors in the columns were, say 1 and 3, maybe with 2 being dependent to 1 and 3, and then 0, 0 or something. Why are we putting, when we're choosing our basis, why do we have to put 0, 0, and why do the other columns have to be 0?
So the question is, when you want to define the matroid, you have to either decide when a set is independent, or it's equivalent to decide when a set is dependent. So if I want to define this matroid M of V, all I have to define are the bases. In other words, I have to decide which triples of columns are independent. Okay. So for example, if I want to decide, is 1, 3, 4 a basis? Well, C1, C3, and C4 form a basis if and only if. This is when I say, basically that doesn't depend on C2 and C5, which is why I forget about these.
So you're just putting zeros in there.
Right.
They didn't have to originally be zeros.
Yeah, they definitely weren't originally zeros.
Okay.
Yeah. So it's just a way of restating how C1, C3, and C4, why they would be a basis. Right. Eric.
Considering the nature of this map, is there some relation, and I saw you actually write it, and then maybe you just didn't want to cause confusion, but is there a relation with the uniform matroid as far as a strong connection between these types of linear matroids and this map in specific?
I see. Yeah, that's a good point. I mean, so this might remind you a little bit of the uniform matroid. For example, when do you have the uniform matroid in this situation? If you pick just some random k-dimensional subspace in Rn, then chances are that all of these projections, all of these different projections are going to be bijective. You know, you have to be very unlucky if projecting onto. I mean, for example, if you're projecting onto the x-axis, okay, when is that not bijective? Let's say that you're in three-dimensional space, okay? You're projecting into the x-axis. When is that not bijective? Yeah, I mean, that almost never happens.
Yeah.
You have to be orthogonal to the x-axis. And there's only one, it's only once that happens in R3, which is in the plane orthogonal to the x-axis. In other words, you have to be unlucky for this map not to be bijective. Okay? If you pick a random k-dimensional subspace, then all of these maps are going to be bijective, and you're going to get the uniform matroid.
So is that true? Unless you have a coordinate kind of plane, then there is always uniform? Unless the subspace you started with was actually the span of some of the basis vectors itself?
We'll see exactly how that goes, but basically, it is true that if you pick a random subspace, it's going to give you a uniform matroid. And it has to be in a weird position, like maybe it's standing on one of the coordinate hyperplanes. That's the kind of thing that can make you have a different matroid. But generally, these projections are bijective, and you get the uniform matroid.
And that's a good example of why you kind of need the fixed coordinates too, because that depends on all that.
Exactly.
In one system of coordinates, you might not get a uniform matroid, but if you switch your coordinates around,
exactly,
you might get it.
Mm-hmm. So okay. So the point is that here I have my description of the matroid of a vector space. Okay. And you guys showed that linear matroids are exactly the ones that arise in this construction. Now, in the way that I stated in the homework, that was an easy exercise. But if I asked you to prove that a linear matroid is exactly one that satisfies this condition, that's not so obvious. But this is the definition that we're going to use now, okay? And we're going to use it to prove this theorem. Okay. And the theorem basically says that duality is the same thing as orthogonality. What does this mean? It means if you have a subspace, and let's say that M is the matroid
Of a Euclidean space.
of.
Or some.
I'll say a little bit more about that. Let's say that we're in Rn for now, and I'll make a comment about what happens if you're not in Rn. Okay. If M is the matroid of a subspace of Rn, then the dual matroid that we defined last time, which is that we defined completely in a combinatorial way, is exactly the matroid of the orthogonal complement of V. Say the orthogonal complement, and this is denoted V perpendicular. Okay. And let me just make a note that I stated this over Rn, but it is going to hold over any vector space. This holds in any vector space. The problem is that in an arbitrary vector space, you might not have orthogonality, but you still have duality. And if you know what that means, then you can just read the proof, and every time I say orthogonal, you think dual, and it's going to work in the same way. Okay? But if you're not familiar with duality of vector spaces, just follow this argument for Rn, and believe me that it's not any harder for other fields. Okay? This holds in any vector space. What is a corollary of this theorem? The corollary is that if you have any linear matroid, then that linear matroid is going to come from some subspace of some vector space. And that subspace is going to have a dual, and it's going to be represented by the dual matroid. In other words, if a matroid is linear, then the dual is also linear. Because if the matroid is represented by V, then the dual is represented by V perp. Okay. So corollary is that the dual of a linear matroid is dual, is linear. Which is one of the questions that we mentioned last time. Okay. So we're going to prove this theorem. So we want to show basically that what are the bases so let's say, let's put it this way. So by definition, M equals M of V. Okay? And what I want to show is that if I look at the matroid M of the orthogonal complement, then that matroid is exactly M star. So what I want to show is that I have a basis of this guy So I want to show that a set S is a basis of M of V star if and only if it is a complement of a basis of M. In other words, if and only if the complement is a basis of M of V. Okay? That way the basis of M of V perp are exactly going to be the basis of the dual M of V star.
I just want to clarify, because I'm thinking that V perp, which we've thought of as the orthogonal complement, you're also talking about is essentially the dual space. Sometimes you're calling it V perp, and sometimes you're calling it V star, and it's because in your head it's the same as being a dual space. Is that right?
That's right. So if I say V perp or V star, I mean the same thing. And every time I'm going to write V perp, and hopefully every time I'm going to say V perp from now on. But I mean, Yeah.
But you're talking about a dual space versus a dual matroid.
Exactly.
Okay.
Exactly. Okay. So what does it mean for? I mean, let's again, maybe it's better if we make this concrete. So let's say that n is 1, 2, 3, 4, 5, and I'm trying to decide if I don't know. Let's say s equals 2, 5, and I'm trying to figure out, is 2, 5 a basis of m of v star, m of v perp? What I want to show is that this is true if and only if the complement 1, 3, 4 is a basis of m of v. Okay. But I was able to describe these two matroids over there. So what does it mean for 2, 5 to be a basis of m of v perp? Well, this is true. So again, let me say I want. So 2, 5 is going to be a basis of this guy if and only if the projection of 2, 5, when I project v perpendicular into x2, 5, that's bijective. So this is what it means for 2, 5 to be a basis of m of v perp. And what I need to show is that this is true if and only if 1, 3, 4 is a basis of this guy. In other words, if I project the dual using the other coordinates 1, 3, and 4, that's bijective. Okay. So this is the statement that I want to show. And you see this is completely a statement about linear algebra, about vector subspaces and projections and things like this. Okay? So let's go ahead and prove this statement. So first let me go in this direction. So this direction. Suppose that when I project v perp onto the coordinates 2 and 5, that's a bijective map. But when I project v onto the coordinates 1, 3, and 4, that's not a bijective map.
Did you switch your? Yeah. Those should be x's. What you have is u's.
Right. Thank you. These should be x's. X. Okay. So one and 2. What does 1 imply? Well, this implies that this is an isomorphism, and so in particular, it implies that if I look at the image of this map, it's going to be all of x25. Okay. Now, what about 2? Well, this projection of V onto x134 is not bijective. What that must mean is that something projected to 0. So suppose V projected to 0. I mean, I'm mapping a 3-dimensional thing to a 3-dimensional thing. The only way that it could go wrong is if I have a kernel. If some non-zero thing mapped to 0. It's the only thing that could go wrong. Now, which things map to 0 under the projection 1, 3, 4? It's precisely the pi 1, 3, 4. I mean, V has to be the projection of V onto 1, 3, 4 puts zeros here. And whatever here. So let me say it a little bit differently. So if V is like this, what does the projection onto 1, 3, 4 do? It takes this guy and leaves this one alone. This one goes to 0, leaves this one alone, leaves this one alone, and goes to 0. Great. Right. So if this guy is 0, that means that these coordinates must be equal to 0. In other words, these ones must have been 0. Okay. In other words, V could only have non-zero coordinates at 2 and 5. But what are the things that have non-zero coordinates only at 2 and 5? They're exactly x, 2, 5. The things that project to 0 under this projection map pi 1, 3, 4 are exactly the things that have zeros here. So V is in x, 2, 5. Okay. So my first thing says x, 2, 5 can be written as the projection of all of this space. The second part says my vector V that I'm considering is in x, 2, 5. So by combining these two, I can say, well, if V is in x, 2, 5, that means that it's a projection of something here. I can write V as a projection of some vector in here. Let's call it little v perp. Little v perp is big V perp. Okay? Is that clear? But this should sound kind of strange to you that I have two orthogonal complements. I'm projecting something onto, projecting something sends me to the orthogonal complement. It shouldn't make much sense to you. And in fact, I'm going to show you that this just doesn't make any sense. So, I mean, here's some vector v perp. Okay. Maybe here's the subspace pi. I mean, here's the subspace X25. And what I showed is that this projection, if I project this guy onto here, this guy is V. Okay. Why is that a contradiction? Because this is V perp. So what is this vector right here? Well, it's V perp minus V, right? V plus V perp minus V is V perp. Okay? And this is a projection. So orthogonal projection. And so these two guys are orthogonal. So V and V perp minus V are orthogonal. But I can distribute, say V of V perp minus V equals 0. But V and V perp are orthogonal. So this is 0. In other words, the inner product of V with itself is 0. But this is the norm of V squared, which is 0. In other words, my vector V is equal to 0. And that contradicts my assumption that V was not equal to 0.
Wait, so how did, with your comment over here, I was thinking I wasn't going to see any inner products. So now I don't see how to generalize that, because you're using an inner product for your notion of orthogonality.
Right, so Jameson's question is what do I do if I don't have orthogonality? And I think I'm going to put that on the forum, and we'll talk about it there, because not everybody is familiar with what things might be involved. But let's talk about it on the forum. How do you fix this if you don't have orthogonality? And how do you do this only using duality and no orthogonality? You can. We'll see. Okay. But so this is a contradiction. It's a contradiction, and so I conclude that this direction is correct. And you're saying I'm done, right? Why am I done?
Duality?
Basically, this is something that we're going to start seeing. So if you're used to other notions of duality, you might know that we're done already, because this is kind of a dual situation where if you prove one direction, the other one is dual. And this is exactly one of those situations where proving this direction is logically equivalent to proving this direction once you have duality. Let me do that explicitly. Okay. So what did I just show? I showed that this statement implies this statement. So let me say that I don't want this anymore. I already know this. Okay. And now what I want to do is prove the opposite direction. Okay. How do I do that? Well, I already proved this direction for any S and any V. So let's apply, let's call this V, this star, and now let's apply star, but instead of S, I'm going to apply it to E minus S. And instead of V, I'm going to apply it to V perp. what do I get? I get that here I have to put V perp. Here I have to put, instead of S, I have to put E minus S. Is a basis of, here instead of E minus S, I have to put E minus, instead of S, I have to put E minus S. And here instead of V, I have to put V perp. V perp perp. Okay? But then we're lucky that V perp perp is V. So it's the sum of V. And E minus S is S. And so what I just showed is that E minus S is a basis of M of V, implies S is a basis of M of V perp. Just that. And so I'm done. And I have proved my theorem. And maybe what I want to do for the remaining 5 minutes of the class is to do this in an example, so that this really becomes very concrete. So maybe what we'll do is consider let's do this in R3, where we can actually draw things. And let's say that our vector space is a vector space consisting of things of the form star, comma, 0. Okay. So this is a two-dimensional space in R3. So this is going to define a matroid. And the bases are going to be pairs. And so the question now is, which are the bases? So is 1, 2 a basis? Is 1, 3 a basis? Is 2, 3 a basis? Well, given this description, what I have to figure out is how this vector space projects on the projection maps pi 1, 2, pi 1, 3, and pi 2, 3. And I have to figure out if those projections are bijective or not. So maybe I'll draw say this is let me get it right this time. So this, so 1, 2, 3. Okay. So the vector space that I'm considering, the subspace is this guy right here, right? This is V. So what happens when I project V onto x12? Well, x12 is the 1, 2 plane. It's V itself. So what happens when I project V onto itself? I just get this is the identity map. This is the identity map. And so it is bijective. And so this is a basis. Yes. 1, 3. So I have to project my vector space V onto the plane 1, 3. Is that bijective? Well, you see, if I project the blue plane onto the 1-3 plane, then it's going to all land on the axis. If I look at the projection of of the blue plane, then the image is the one axis. This is not bijective because it takes a two-dimensional thing to a one-dimensional thing. So this is not bijective. And so this guy is not a basis. Okay? And what happens when I project onto the 2-3 plane? Then I'm projecting in this way, and so when I project over here, the image is the 2-axis, which is one-dimensional, and so again, this is not a bijective map. And so this is not a basis. Okay? So the matroid that I define here has ground set 1, 2, 3, and it only has one basis, which is 1, 2. And so, again, the point here is that linear matroids, we have two descriptions for them. One is in terms of a vector configuration. The other one is in terms of a linear subspace. We showed that these are equivalent, but they're somehow psychologically different. I mean, thinking about it in this way sounds very different from doing linear independence of vectors. They're equivalent, but it's.
I think it's partially why it's so different in our brains is because of Eric's question. Like, if you think about it like this, you just think of uniform matroids a lot.
And for example, in this case, I didn't get the uniform matroid.
Yeah.
And the reason is because this vector space is clearly not generic with respect to these arrows. But if you pick any vector space that doesn't point in a way that is special towards, start again. If you pick any subspace that is not in special position with respect to 1, 2, and 3, you're going to get the uniform matroid. And it's only vector spaces like this in very special position that give you other matroids. Okay, that's a good point to stop.
I can give you money. Should I look for you tomorrow?
Yeah. I think there's a meeting in Compton at 1:30.
There's one thing that I haven't really said, but I want you guys to understand, which is that you can use the form to talk about the homework also.
Before we turn it in?
Before you turn it in, I don't want to see any complete solutions on there. I don't want to see, here's the solution, copy it down. But if you guys have some partial ideas and you want to discuss them, that's perfectly fine also. And if you want to discuss with the people in Colombia, that's perfectly fine also. You realize by now that these homeworks are not